So let's try this. You have HPO phosphate, HPO4 2 minus, H2PO4 negative. Okay, they only differ in one. They differ in charge and they differ in the number of hydrogens, right? But the size should be more or less the same because your hydrogen doesn't make much difference in terms of size. So which of these has the smallest Kb? A, B, or C? Smallest Kb. Smallest Kb means weakest base. And weakest base means most stable base. Most stable base means most charge dispersal, right? Or lowest charge density. Lowest charge density would be, very good. How about the next one? Which of these is the largest Ka? So largest Ka means the strongest acid, right? Which one is the largest Ka? Largest Ka would be the conjugate with the of the weakest base, right? Very good. Okay, so this is the conjugate base of it. That's why in the stepwise ionization, if you have H3PO4 gives you H plus H2PO4 minus, and then you have H2PO4 minus gives you H plus HPO4 negative 2, and HPO4 negative 2 gives you H plus phosphate. Okay, what are the KQs for this? K1, Ka1, Ka2, and Ka3. Generally, what you find is Ka1 is typically much larger than Ka2, much larger than Ka3. Okay, and I think I gave you numbers for phosphate, pKs earlier. Let me see. Right here, silver phosphate. 2.15, 7.2, and 12.35. Okay, so you can see K1 and K1 is much larger. K1 is 10 to the negative 2.15. That's much larger than 10 to the negative 7.2. Much larger than 10 to the negative 12.35. Okay, so in the stepwise ionization constants of a polyprotic acid, they usually decrease a lot from one step to the next. Which one's a stronger acid, A or B? HBRO or HBRO2? What's HBRO? This is BRO minus. This is the bonding here. Okay. And this is HOBRO2. So, oh, there's no O here. Okay. HOBR. Right there. And how do you complete this structure right here? How do you draw the structure of BRO2 minus? You remember? BRO2 minus. How many valence electrons do we need to show? Bromine should give you 7, right? Oxygen gives you 6. 6 times 2, that's 12. And the negative 1 gives you an extra 1. So 7 plus 12 plus 1, that gives you 20. 20 valence electrons. So what do? I try to do an octet around each one. That gives me 16, right? 8 on this side, 8 on that side, so 18, 20. Okay, so that would be that takes care of the 20, but let's look at formal charges. What's the formal charge for bromine here? This is the charge of negative 1. What's the formal charge of bromine? How many does it appear to own here? That's 2. Okay. 2, 4, 6, 8, half of 8. 2, 4, 2 lone pairs it owns. and then half of the 2 pairs would be 2 singles. So it appears to own 6. By itself, it would have 7, right? 7 minus 6 is plus 1. So you can lower that formal charge by putting one of these lone pairs in. So HbRO2 would have this structure right here. Okay. So anyway, which one's the stronger acid? HbRO or HbRO2? A or B? You compare the bases, right? The bases are both negatively charged. They have -1 charge. Same charge, so you look at the size to do the charge density. Which one has a smaller charge density? Okay. So let's see. Very good. HbRO2. Okay. This is larger, smaller charge density. So BrO2 minus would be the weaker base. The more stable base. The weaker base, its conjugate would be a stronger acid. A good way to remember this trend right here. So you say HbRO is going to be weaker than HbRO2. It's going to be weaker than HbRO3. It's going to be weaker than HbRO4. A good way to remember this is to just remember that HClO4 is one of the 6 strong acids, perchloric acid. So, and all the other acids then, so HClO then you would expect is weak, right? So it's weaker than HClO4. Did I mark this one? I didn't mark it, right? So explain why HOI is weaker than HOCl. Okay, HOI versus HOCl. So let's compare then OI negative versus OCl negative. It's both negative. They're both negatively have a charge of -1. Which one has a greater charge dispersal? Or lower charge density. You'd think iodide is bigger, right? Bigger size. Right? So you'd think it'd be more dispersed. And so you might think that this would be a more stable base, right? And so HOI would be a stronger acid. Right? But HOI is a weaker acid than HOCl. Did we just get into a contradiction here? We just did, but there's a way out of this. You can still use the charge density argument here in the fact that the bond between oxygen and iodine is, and oxygen versus chlorine bond are polar, right? Which one's more electronegative? Chlorine or oxygen is more electronegative than chlorine. Chlorine is more electronegative than iodine, right? So this bond right here, okay, is what? More polar. Bigger difference in electronegativity between oxygen and iodine. This is less polar. Where is the polarity directed at? Towards the oxygen. Oxygen is more electronegative. So we can say in a sense that because this bond is more polar, okay, we can say that the charge is concentrated more in oxygen. Because that bond is more polar. So in a way, you have a higher charge density on the oxygen, which would make more impact on the ability of your molecule to lose a proton, because now you would say that this would explain the opposite effect, the opposite observation, right? So charge is more concentrated in the oxygen, so this would be the less stable base.